Hello, everyone. So my name is Kendall Green, and I'm going to talk a little bit about isomers. And my goal is to help you understand what isomers, at least the different types of isomers, and how to identify them. And yeah, so let's get started. Now let's go ahead and share my screen. Also going to I'm going to start a little timer here so I know how long I'm going. Okay, so let me start this presentation, and here we go. Isomers. So, the isomers. The word comes from the roots isos and meros, which mean equal parts, and that's fundamental because isomers share equal parts. So, what are isomers? Great question. The best way I've found to describe them is like Legos. I like Legos. I played with them when I was a little kid, and I would just build armies, cities, whatever I felt like. And the thing is that when you have a set like you see here, it has the same number of pieces, and you can do whatever you want with it. As you can see in this set, you can build a dump truck or I don't really know what that is, but some type of lifting vehicle. And like isomers are molecules, as you can see in the little box. They have the same chemical formula, they just have different molecular structures. So that means that basically, just like you have the same building blocks, so you have the same number of carbon, hydrogens, and whatever other atoms there are, and they're just rearranged differently. And so, because there are many different isomers, scientists have come up with fancy ways to name them all. So here we go. But before we get into isomers, I want to talk a little bit about why are isomers important, and also why do they form? Because I don't know, but when I was studying this, I asked, well, why do isomers even exist? What's the point besides making chemistry harder? And the biggest main reason is because it's all due to timing and energy and the surroundings that the molecule finds itself in. Those all have different effects that can cause a molecule to go into a different type of isomer, and so it's just the surrounding energy and time and the time where it's at that helps determine what shape it takes. And the biggest reason I know of why they're important is because it keeps us alive. And you can see in the background here, and that's a protein. And proteins, their shape determines their function. And in order to have your cells running well, they need to have specific proteins. And so while proteins share the same building blocks, they have different shapes that perform necessary functions that keep us alive. So thanks to that, we are living. So they are very important. And so let's continue on to the different types of isomers. So the basic type is one that, that will be, at least for me, is the easiest to understand. It is constitutional isomers. And constitutional isomers basically just are the same molecule. They just have things rearranged a little bit. So you can see that this fluorine atom right here and that fluorine atom down there have been changed. So it's still the same molecule. The molecule on top has 3 carbons. 1, 2, 3, 4, 5, 6, 7, 7. Oh, write the hydrogen before. 7 hydrogens. And it also has 1 fluorine. The same with the bomb. It also has 3 carbons. 7 hydrogens, and 1 fluorine. So there's really no difference in chemical formula between these two. However, the difference is that they do have the fluorine atom has changed position. So that's the basic constitutional isomer. The things you gotta watch out for is that you want to make sure that if you're given a question, say what are the constitutional isomers for this molecule, is basically you want to make sure you get the molecular formula right. Now another danger is with you can incorrectly write an isomer. So let me clear everything away. So I know this because while preparing for this video, I wrote an isomer incorrectly. And so let's go ahead with this atom. So I'm going to write in a compressed hydrocarbon fashion, or basically where I just have lines. And those lines represent every tip point end of a line represents where a carbon atom is. Okay, it's 1, 2, 3, 4, 5, 6. Okay, so 1, 2, 3, 4, 5, 6. Yes, so there's a carbon atom here, carbon atom there, carbon atom here, carbon atom there. There we go. So that's a terrible 6. I'll make it better 6. And there's a carbon atom there. Now also remember that there are also hydrogen atoms that just are not written in. So for example, at this number 6 carbon atom, there would be 2 hydrogen atoms attached. They're just not written in. Then at this, for example, this 1 atom, there would be 3 hydrogen atoms as well. So you can count up, we'll go ahead and count this, the molecular formula for this. So you can see that there's 7 carbon atoms, so 7 carbons, and then there should also be, so we got 3, 5, 7, 9, 11, 13, 16 hydrogen atoms. I know you couldn't see me counting, but basically I was just going along the lines, counting 3 for the ends and then 2 for each carbon in the middle. So there we go. There we have it. So I'm going to erase some stuff to make it a little more neat. Okay. So there we go. So we know that there are. Rewrite that one. So we know this chemical formula. So what's an isomer? What's a good isomer? So we can just go. So usually you just want to write one short, and then you can replace. You can put one somewhere else. So there we go. So this still has 1, 2, 3, 4, 5, 6, 7 carbon atoms, and there's also 3 on this where the 7 is. So that's 3. There's 2 hydrogen atoms there, so that's 5. 2 hydrogen atoms, 7. 2 hydrogen atoms there, 9. There's only 1 hydrogen atom there, so that's 10. And then this is 3 there, so that's 13, and 3 there, so that's 16. So we got 7 carbons and 16 hydrogens, just like before. So there you go. We've got a good isomer. Now, important thing when you are drawing isomers is that you want to be careful of accidentally drawing an isomer. That was a terrible 3 down there. You want to be careful of drawing an isomer that you've already drawn. So, for example, with this one, I mean, the best way I found is just to be careful of where you've put the atom already. So, for example, with the isomer I've already drawn, I will just go ahead and I could, if I were to draw an isomer that looked like this, 1, 2, 3, 4, 5. So you have the same structure and then just go like that. Now, if I were to rotate this, it would actually be the same. So just rotate that, I would get the same isomer as before. So you have to be careful that you don't do that. So this, so be careful that when you're trying to write an isomer that you're not making that mistake. And that you do, and I found the best way is also to just count from the endpoints. It helps me figure out if I've drawn a correct isomer or accidentally copied another one. And that's really constitutional isomers. They're pretty basic. Just think of a Lego set or whatever works better for you, and just rearrange them and as long as they have the same pieces, they're good. Now, we're going to get into stereoisomers, and they're a little more complex in that they, instead of being rearranged like Lego blocks, they just take up a different spatial arrangement. So in order to show this, I have some models, and we're going to start with this little picture in the right here. So these are enantiomers. I just think some bookworm name like Antionum, and kind of comes to mind this type of stereoisomer. And at first glance, they may look exactly the same because they have the same atoms, so they've got the same chemical formula, but they look like the fluorine and chlorine and bromine atoms are in the same place. But if you can tell, this line right here shows that there's a mirror image. So there's a mirror image of these two. So they're actually just kind of, if that line was a mirror, they would be reflected. Sorry, the left atom would be just would be a reflection of the other one. So that's basically what it is. It's just a reflection. And as reflections go, they may look similar, but let me just go ahead and put us into, let me stop sharing for a moment, and then you can focus on, see the big picture. Here's the two atoms that look like they're mirror images. So we've got purple in the same place, yellow, green back here, white on top, so look the same. We may think, it looks so similar that maybe I can just, if I just twist this, I can just get those to match up. Now, if you kind of see the problem, the green's in the right place, but the purple and the yellow have been switched. So the yellow one is in the back, while this yellow one's in the front, and the purple is in the front back here, although the purple is in the back here. So these actually two atoms have switched places. Now, this is not a constitutional isomer because they're still attached to the same carbon atom. If I were to like take this atom and attach it to a white atom on top, or take it over here, that would change things. But they're still attached to the same carbon atom, so they are stereoisomers. They just have changed the way that they are arranged in space, or in space, I guess. That's not actually changing their different connections. So that is an enantiomer. So go ahead and go back to sharing the screen again, because that's like my PowerPoint presentation back. So there you go. Another thing that you should know is conformers. Conformers are basically atoms that are rotated around a single bond. So it could be a single carbon-carbon bond or a sigma bond. A sigma bond is just basically a single bond, and that's basically what conformers are. And you also see the word rotamers. I'll go ahead and show that as well. I'll just stop sharing. So the best way I can show a rotamer, and this is how I understand it. So you're always free to look up for more information. You shouldn't really have to worry about these. I don't think, because the professor never mentioned them. I just like to bring them up. just in case, but this is also kind of covers a conformer as well. So if you look at these atoms, so now it's the same all just put together, and you can argue, so they look the same, but if I twist this, it's technically taking out a different spatial arrangement. Now, there is an argument that there are arguments that this technically is still the same molecule because there's still the same connections. And it may have changed the same spatial arrangement, but it's just twisted. So some say it doesn't count. And you won't really need to worry about this as much. But you should know that things can be twisted. And say if this purple atom had like another connection up here, and then another connection up there. And then if you were to rotate that, that would make a different spatial arrangement. So that would be, that could also change the spatial arrangement of the molecule. So keep that in mind, and that's a conformer. So we'll go back to screen sharing. Look at my time. And the last one we'll go over is diastereomers. So diastereomers are actually cover conformer and cis trans isomers. Cis and trans isomers are actually pretty simple. And so I'm just going to go ahead and let me annotate computer. So here we go. It's really a cis isomer just has two equal groups on one side of a double bond, a double carbon bond, or at least a double bond. So as you can see, it's not really hard in that case. A trans just has two opposite groups, or this two groups that are opposite a double carbon bond. That's really it. But I'm going to go ahead and show you a trick that is very important in order to, it can help you understand why, or it can help you identify molecules that are way more complex because they may not be the simple pictures that you see here. So I'm going to go ahead and clear all my drawings. We're going to go ahead and going to go to clear, stop, and we'll go ahead and we're going to go to chiral centers. Now, if you've heard of chiral centers, you may think that that's just a very confusing word, but chiral centers aren't terribly confusing. They can be, but for the most part, you just need to know that it's one carbon atom attached to four different groups. It can sometimes get complicated when you get into like large molecules like this. And one thing to be careful of is that this is technically a this would not be a chiral center, but for example, see if I were to do something like that, then you could say that this is a chiral center right there, because there are four different groups, because there's the hydrogen atom, then you have this branch right here, you have this branch right here, or this branch right here, and then another branch right there that is attached to. Now, if it was just a circle, that doesn't really count because you've got like, just when in circles, it goes all the way around. So if it goes all the way around, that doesn't count. But if you have something branching off that circle, it does count. So just keep that in mind that circles can be tricky. But chiral centers are basically just a carbon atom surrounded by, connected to four different groups. And going back to the simple example, the chlorine, I had the chlorine, bromine, and the fluorine, and the hydrogen atom. They were all, that is a chiral molecule. And what you can notice, the important thing to notice is that depending on how the chiral centers have been changed, can help you understand what a molecule is. For example, I'm gonna take a I'm gonna erase this. But if all, I'm gonna show an example. If we're gonna clear all drawings, okay? So, for example, if you have a molecule that looks like this, and you see this, okay, so we got bromine up here. Then we're gonna look at this one, make sure it's the same amount of atoms. Now I'm gonna use this. So if you look at this, the chiral center has been changed because it switched position a little bit. The atom didn't necessarily, it went, so the arrow, the solid arrow, means that the bromine atom is going into the page, while the dashed line means that the bromine is coming out of the page. And that means that it was switched. So once you switch a chiral center, and if all the chiral centers in a molecule are changed, it usually ends up in an enantiomer. Now, there are exceptions to this. For example, if I have this, let me do a better job than that. If I have this, if this molecule and I switch the chiral center, so I go from here and then I go to this, go to here, and I switch this. Now that is actually, if you just flip this atom over, it's actually the same molecule. You can try flipping this molecule to get over, but you will not, it will not be the same. So this is an enantiomer. So this is enantiomer. This on the left, the one on the right is not an enantiomer. This one is the same molecule. So that's one way to help you identify enantiomers. Another thing is that it can also help you identify a diastereomer, so not an enantiomer, basically. So if you have a molecule like this, and say we've got two chiral centers here. Okay, so I'm going to change, if I only change one of them and leave the other one unchanged, because only one has been changed, if only one of them has changed, then it's not a chiral, not an enantiomer. This is a diastereomer, which I'm really bad at pronouncing, so hopefully the professor forgives me. But this is a diastereomer. Because the chiral molecules, only one has changed, and these are not the same. You can try flipping these around, but they won't. So that's the basics. Go ahead and memorize the form, but I highly recommend trying to understand this chirality thing. It helped me. And to top it all off, I have some, if I can move my PowerPoint, I have these recommended videos. These are what helped me really understand isomers. So if you're struggling with them, I recommend one of them. If you want understanding conformers a little bit, I recommend the third one down. That one, this one is a lot about conformers, and just kind of help me understand the entire Rodemer conformer thing. But these other two are great for understanding just stereoisomers and chirality. So with that, thank you so much for watching this video. Good luck with your future exams, and thank you very much. Yeah. So we'll go ahead and clear and finish this video. Yeah. Bye.